Hello everyone, my name is Fasil Cheema and I will be presenting our work, Precision Recall Cover, a method to assess generative models. This work was done as part of my master's thesis at York University under the supervision of Dr. Ruth Urner. To start off, let's outline the problem. Generative models have seen enormous successes as we all know in the last couple of years. A critical challenge is finding a principled way to assess how good a generative model is performing. A challenging aspect here is that many generative models, such as GANs, do not come as explicit probability distributions, thus making their evaluation quite difficult. A recent work has proposed a twofold direction in the pursuit of solving this task. A metric should be able to be informative on the quality of the generated samples, and as well as the diversity of the samples generated. Two of the earlier measures for evaluating GANs are the Frichet inception distance, the FID score, and the inception score, IS. Both these scores are still currently among the most popular metrics for assessing generative models. However, the literature also notes some serious shortcomings. FID does seem to capture the quality of the generated samples. However, it does not provide adequate information on the diversity of the samples as stated in some prior works. Inception score, on the other hand, ignores the true distribution and has access to just the generated samples and does not compare to the true samples at any point. We'll now discuss the work mentioned before that seeks to address the shortcomings, and these new methods both seek to judge the quality of the generated samples and the diversity of the generated samples. The first of these works is Precision Recall, written by Sajadi and colleagues in 2018. This work incorporates both diversity and quality of the generated samples. This work has several pros. It comes with a very nice theoretical foundation. It's intuitive and it's informative. It also seems to do a good job at capturing the diversity of the model. However, some cons are it lacks a clear algorithmic implementation. The standard choice of implementation of this method uses k-means clustering, which is sensitive to random initialization. This is quite problematic, as some works have pointed out. So we now move on to those said works. Improved Precision Recall, written in 2019. This work seeks to rectify this by adjusting the algorithmic implementation, so they use k-nearest neighbors instead of the k-means clustering algorithm. However, as some recent work, such as Naeem and colleagues in 2020 point out, we will later see in this experiments as well, this method is quite prone to be over-accepting, and thus is prone to giving inflated scores of both precision and recall, quality and diversity. Think of those words as synonymous throughout this presentation. As we see in this figure, improved precision gives a score of 0.86, and improved recall gives a score of 0.68. These scores indicate that these two distributions are very similar. Clearly to us, these Gaussian distributions, visually, although they overlap, are not that similar. The next work is Density and Coverage, written by Naeem and colleagues in 2020. This work does seem to be better at not being as overly accepting of outliers as improved precision recall. However, it still has some drawbacks. The scores are not normalized, and we will see later this method can exhibit scores that are quite high. And although an improvement in being less overly accepting, it still does seem to suffer from this issue as well. We're now going to clearly define the problem of precision recall. In prior work, Sajadi and colleagues, and the follow-up works that are subsequent to that work, define precision as the part of Q that the generated distribution is covered by P, the real distribution. In this example, we will see that the red sphere, that in this case we'll call that the generated distribution, Q, synonymous in this case, is encompassed completely by the blue cube, the real distribution, P. So all of Q is covered is by P. We would say this generative model to be highly precise, as the sphere is fully encompassed by the cube. Similarly, recall is defined as the part of P that is covered. Since the better recall, the more diverse, the bigger part of Q can be used to encompass P. I know that seems like a lot, but let's look at the figure to explain this. In this example, note that the generative model does not cover all of the true distribution, i.e. the sphere doesn't cover the whole cube. There are regions of the cube that the sphere will never touch. We can therefore say it does not completely cover the whole diversity of the true distribution. Now, using this intuition, we will define a population level measure that will then motivate our algorithm. We define precision cover as a proportion of balls with Q probability mass beta that also have at least probability mass alpha, with respect to distribution P. Likewise, recall cover is defined with the distribution swap. Now, intuitively, these parameters, alpha and beta, will provide knobs. Beta is considered the amount of probability to deem a ball to have sufficient probability mass, probability with respect to Q, and alpha is a knob to consider what mass we consider as a cutoff for a negligibly small probability mass. Now, if you look to the figure at the bottom, we can see in this simple example, the green ball has enough probability mass with respect to the red distribution. However, the blue ball doesn't. This simple example motivates our search to highlight regions with sufficient probability mass with respect to both distributions. A nice property of our population level measure is that it also seems to converge to the joint support of the two distributions given sufficient samples. Now, this theoretical foundation we've outlined directly leads to our practical algorithm. Our version of precision cover is simply the fraction of k prime nearest neighbor balls with respect to the samples from Q that contain at least k points from the samples from P, and vice versa for recall cover. Our algorithm is literally equivalent to our population level measure, however, using the sample sets instead of the true distributions of generative distribution and the true distribution. Thus, this quickly motivates a direct algorithmic implementation from our population level measure. Now, with the algorithm, we also provide several favorable theoretical guarantees. In the first theorem over here, we show that if both distributions are the same, we expect with high probability that our precision cover score will give a value of 1. We also have analysis to show our algorithm enjoys a nice property of being locally consistent for regions with joint support. This is seen in the second theorem. This theorem can then be used to show that our method also enjoys support consistency in the third theorem. That is, with high probability, our method will identify regions of joint support for enough samples from both distributions. There are many potential practical implementations for Pro's method. We believe that our formal analysis sets our work apart from earlier suggested methods. We believe that having clear population level measure with empirical analog and statistical guarantees on how they relate is quite reassuring to those who would like to use our method to diagnose, improve, and grade their generative models. We're going to go on to our experiments. In this section, we'll show that experimentally our algorithm also shows some promising behavior. With two Gaussians that are partially overlapping, our method reflects the slight partial overlap as seen in the figure to the right. You can see the scores at the top. Improved precision and density give high scores for partial overlap, whereas only our method correctly identifies only a partial overlap and gives a lower score of 0.13. It can also be seen here that it has other issues too, such as incorrectly identifying two completely disjoint distributions as similar. In this case, we have the red samples, which are from the generative distribution, we'll say. This is a uniform distribution in the shape of a donut. And we have a blue distribution. This is in the shape of a sphere within that donut, but these are disjoint distributions. Only our method here correctly shows scores that reflect the disjoint nature of the two distributions, where the donut distribution never actually touches the sphere in circles. We can see that the original precision recall method incorrectly rates these two as very similar, and even the newer methods do not correctly identify these two distributions as disjoint. You can see this from the scores at the top. And the PR curve that's mainly filled in indicates high precision and high recall, especially relative to completely disjoint distributions. Have another set of experiments where we use a simple setting to have true values of precision recall. In this case, we define true precision as the overlapping volume, the joint support between both distributions, divided by the volume of the generated distribution. Since they're uniform, distribution of probability mass and volume are proportional, and we define the same thing for true recall. Obviously, the definition altered. And below, you can see the figures. Over here, we show that these are uniform distributions, and we alter the true precision recall by altering the overlap in this case. Now we start the convergence experiments. We control for the number of samples. So we set a number of samples, we sample those, and then we generate the two distributions in Python. We compute the scores of precision recall curves, cover, improved precision recall, and density and coverage. We then see how they match up with our mutual true definition. We can see that as dimensionality increases, we see that our method, which is the green, converges faster to the true value, the orange dotted line, and red is improved precision recall, and blue is the density and coverage metric. and you can see the other scores in the paper. But from this trend, it seems quite evident that our metric seems to converge faster to the true values. Our next set of experiments are quite practical and apply directly to real-world settings. We start off by using a generative model that already comes equipped with a built-in way to assess quality. VAs are trained to minimize the KL divergence, and we should expect that after each epoch, the set of generated samples should be of higher quality. So what we do is using MNIST, we train a simple VAE. After each epoch, we generate 10,000 samples and run all comparable quality score metrics: precision cover, improved precision, and density. We then see if the metrics align with expected behavior. Epochs, you go through an epoch, the quality of your samples should be better. We see that sample quality subjectively does seem to increase. However, only our method agrees with this observation. Density is not normalized, and we can see that here, as it gives an uninformative answer, as does improved precision, which is overly accepting and just gives a perfect score throughout the whole experiment. Next, we designed a similar experiment, but now to assess the diversity of comparable metrics. We use the MNIST dataset and split into two sets. One set we will call the generated set, and the other is the real set. For the generated set, we progressively increase the number of digits that are dropped, thus decreasing the diversity of the sets. So for example, you'll take out zeros, twos, threes, right? You progressively drop these digits. So the generative set will never have those digits. You're decreasing the diversity. We then sample the same number of samples from both sets and compute diversity type metrics: recall, cover, improved recall, and coverage. Most methods tend to align with the expected behavior. However, each time we drop a digit, roughly the expected loss of diversity is about 10%. We see that our method most closely agrees with this. Now we're going to move on to high quality images. This is an application of GANs. We will artificially lower the quality of images via downsampling and linear noise schedule. And we'll compute the quality type metrics, precision type metrics in this case. And in this experiment, we see all methods see a trend of decreased quality, precision. However, as noted prior, improved precision is quite overly accepting and density is not normalized. And it should be that seen here subjectively, you can see the image quality degrade as well. For the next slide, we'll also use GANs. We'll apply our method to GANs more specifically in this case. We use a commonly noted observation on GANs. This is the truncation trick. As the truncation of a GAN decreases, we expect a GAN to start outputting samples that are more diverse, but of worse quality, and vice versa for increased truncation. The experiment was conducted for the improved precision recall paper as well. And you should see this phenomenon follow through in both cases. So this is ideal behavior as expected with some experimental papers seen before. And our work alongside with improved precision recall, which is the bottom figure, our work is PRC scores, which is the top figure. They both seem to follow this trend of the diversity quality trade-off. Now we'll also use GANs to create a generated set of samples and the FFHQ data set. We also, now in this case, we're going to use GANs to create a generated set of images, and the FFHQ dataset in this case will be the real dataset. We will then compute all comparable metrics: precision recall cover, improved precision recall, and density and coverage, with varying choice of K for this experiment. Note that all these methods will use the same core K&N computation. They all have all these methods have access to the exact same information, and we can see that for the same set of generated and real images, as we change the value of K, so there's no new computation done. All these methods are using the same core K&N method. The score changes for the other methods, but our method is robust to the choice of K value. Our method is the green line in this case. Red is improved precision recall, and green is the density and coverage. Green is our method. Red is the improved precision recall, and blue is the density and coverage. This is a nice property, the robustness. As you can see, the green line doesn't change too much. That's our method. This is a nice property for practitioners who don't have to additionally worry about how sensitive the results will be based on some arbitrary choice of K. And we hope that this is something that makes it easier to implement to diagnose generative models in the real world. Thank you so much for listening to our presentation, and we would like to acknowledge that our project was funded by an NSERC Discovery Grant and our association to York University and the Vector Institute. Thank you so much.